All right, our next section, we move on to chapter 7. So 7.3. If you're taking trigonometry, you probably recall this. Trigonometric equations. They don't get too difficult in here. Probably not as complicated as they were in just a regular trig class. But you still will use some of this stuff, especially in calculus. So you still need to kind of refresh your memory on how to solve some of these trig equations. So let's just do a simple linear format equation. If I have 2 times the cosine, let's say theta, minus the square root of 3 is equal to 0. If that was just 2x minus square root of 3 equals 0, you solve it just like you would normally do a linear equation. Isolate the variable x. For this case, we want to isolate the trig function cosine. So I'm going to add square root of 3 to both sides. Then divide by 2. So I'm looking at the cosine of theta is equal to the square root of 3 over 2. I need to solve for theta. So give a solution for theta as a general formula. All right, so you got to remember cosine along 1 full revolution around the unit circle has square root of 3 over 2, positive, in 2 locations. Quadrant 1, all right? And then also quadrant 4 is where cosine is positive, right? So we want to know that angle too. So we're going to have 2 basic formulas for theta. One we're going to use for the quadrant 1 angle plus all 4 revolutions around it, meaning all coterminal angles, right? That's the general solution. So you have to ask yourself, what angle in quadrant 1 has its cosine value equal to square root of 3 over 2? Don't remember, huh? Okay, if you don't remember, you can use your calculator as an aid, right? So you say what angle in quadrant 1 has cosine equal to square root of 3 over 2. Well, I could say, I know that the inverse cosine of the square root of 3 over 2 would give me my answer theta. Now I'm using my calculator as an aid because the answers displayed in the calculator for inverse trig functions don't necessarily mean those are the answers that are what we're looking for. Remember, especially inverse sine can yield negative angles, right? Remember that? That's what your calculator will show. Maybe we're not interested in the negative angle. All right, so bring the calculator back. If I do inverse, put my calculator in degree mode so you can recognize the actual degree and not the radian measure. So second cosine brings inverse cosine. Square root of 3 over 2. That's my square root. Uh-oh. Square root of 3. Get out of there. I got an arrow out to get my division of 2. There we go. And I see it's 30 degrees. Okay? So you probably remember it was either 30 or 60, right? All right, so the quadrant 1 angle is 30 degrees. So quadrant 1 is 30 degrees plus all 4 revolutions around it. So 1 full revolution is 360. So 360 degrees times Now, some books use K, some use N. It doesn't matter to me. Just pay attention to what my math lab may want. This uses, I don't even see it on them. Let's say N. So 30 plus, get off there. 30 plus 360 times 1, 30 plus 360 times 2, and so forth. There's an infinite number of answers for that quadrant 1 answer. The quadrant 4, well, 30 degrees is a reference angle, right? So reference angle made with the x-axis and the terminal side that we have in quadrant 1 at 30. So it's also 30 degrees negative, which means it's shy 30 degrees from a full 360. So the quadrant 4 is 330 degrees plus all 360 revolutions around it. That's a general formula. So n could equal any integers, basically. I can go positive rotations, I can go negative rotations, you still always end up in the same location. So n is any integer. All right, I solved this equation in degrees. Sometimes they want you to express this in radians. Well, just know your conversions. I usually always work with the degree first and then convert everything back, however you want. So 30 degrees as a radian is pi over 6. So theta could be pi over 6 plus, not 360, but 2 pi, right? 2 pi in. And then 330 is shy a full 2 pi, 30 degrees or pi over 6. So that makes 11 pi over 6 plus 2 pi in. Again, it could be N, it could be K, it could be any letter that you want. Every textbook's a little bit different. Yeah, 11 pi over 6. Yeah, we'll do one more and then we'll call it a day, right? Let's say list the solutions. Find all solutions on a specific interval. Zero to 2 pi. Zero is included, 2 pi is not, but up to 2 pi, right? So that's one full revolution. Square root of 3 tangents times 3 theta plus 1 equals 0. All right, so every teacher teaches trig equations slightly differently. I like to keep every type of equation kind of consistent. That if I know I can come up with a general solution or formula, then I can use that to find the specific answers. Now, right here we have more than just theta, 3 times theta, right? So you can make a substitution here if you like. That's kind of what I like to do. I just say, okay, 3 times theta, 3 times an angle is still an angle, right? So I'm just call it an angle. Let's just say let alpha maybe equal 3 theta and rewrite the problem. That way you don't have to keep in the back of your mind 3 theta is this. You just work with just another angle. That's not 3 alpha, that's just alpha. Sorry. 3 theta is alpha. Now we're working similarly to a problem we had just now. Get the tangent by itself. So I'd subtract off 1, divide by the square root of the 3, and that isolates tangent of alpha. Now you leave like that if you want to, but you can rationalize it too if you recognize it. That's a negative square root of 3 over 3, right? And of course, again, if you don't remember, we can figure it out with the calculator to see what his degrees value would be. So if I do second inverse tangent of a negative square root of 3 divided by the 3 tells me a negative 30 degrees. Well, negative 30 is not on the interval that we're looking for. But if I would draw a picture really quickly of where negative 30 degrees is, it's that, right? Negative has a clockwise rotation on the positive x-axis. That's negative 30 degrees. That's the same thing as a positive 330. But there's probably another quadrant I got to consider too, where tangent is negative. Tangent is also negative quadrant 2, directly 180 degrees from it. So we've got quadrant 4 and quadrant 2 have the same tangent values. Well, if you're 30 degrees shy from this x-axis, you're 30 degrees shy from this negative x-axis, right? So this is 150 degrees, right? All right. So alpha is equal to 150 degrees plus all full revolutions around it, right? So that's 360 degrees. I'll put a K this time. And alpha is equal to the 330. We solve for alpha. Well, that's not what the problem had us to solve for, right? We need to solve for theta. Well, just what is theta? Alpha is 3 theta. So make that substitution back. And if I divide everything by 3, that solves for theta. So I get 2 general formulas. Theta is 50 degrees plus 120 degrees K. And this one is 110 degrees plus 120 degrees K. I use these formulas, plug in numbers for K, or N if you wish, to see if those answers I get fall within the interval. All right, so now choose values for K. Start off with 0, that's always the easy one. Theta is 50 degrees and 110 degrees. K is 1. These are usually pretty easy to calculate. All right, that would be 170 degrees, and this would be 230 degrees. So you can kind of just keep on going. All we're doing is keep adding 120, right? That's all we're doing. K is 2. 120 added to 170 is 290. 120 to that one is 350. If I go one more, you can see I'm going to be more than 120 right here. We'll make that 410. And then that would be 470. These two are too big, right? Outside the interval. So we got 6 solutions here. Kind of gives you a little bit of a hint. Our argument was 3 theta. Right. If it was just theta, we get 2 solutions. So 3 theta, we got 6 solutions. That's kind of how you know how many to expect. If they ask you to convert this into radian, y'all remember y'all conversions? 50 degrees times pi over 180 is the conversion factor. And you can simplify that. That's going to be what? 5 pi or divide everything by 10. 5 pi over 18. Do the same thing for the 110 and so forth, right? All right, we'll stop right there and we'll do a couple more problems. Trig equations. Again, this is kind of just a refresher, hopefully, if some of you, hopefully you've just taken trig and it's still kind of fresh in your mind. Hopefully it hadn't been too long since you've seen this. But we can also figure out how to solve these using the graphing calculator, using that intersection method too. We'll work through some of that too on Thursday. Any questions? I think